Hello everyone. In this video, we'll, uh, we'll present you magnetostatics, and this presentation includes the basics of magnetostatics, basic definitions, and Biot law to calculate the magnetic field intensity at a given point, and the Gauss law of electrostatics, Ampere's law, and their applications. I mean, to find the magnetic field, magnetic flux density due to these two current carrying sources. One is a one-dimensional source, I mean infinite long straight conductor, and infinite sheet of current, which is two-dimension. First, we'll see the basic definitions of basic concepts of magnetostatics. So magnetic field is in generally produced by either a current carrying conductor, or it can also be produced by a permanent magnet. So it is some region which is, I mean, magnetic field is a region which is produced by a current carrying conductor and or a permanent magnet. In that region, there will be a magnetic effects will be existed. Magnetic effect in the sense the magnetic force will be existed, and because of that magnetic force, if any other magnetic material is placed in other magnetic material is placed in that region, it will feel that experience, it will feel that magnetic force. Now, but in magnetostatics, now we specifically focusing on the source for the magnetic field is a current carrying conductor. Sorry. So throughout the video, the source for magnetic field is a current carrying conductor. But here we specifically mention that current is a steady current. What does it mean by a steady? I mean, the term itself is a little bit very interesting. The general meaning of steady in the sense static. General meaning of steady in the sense static. I mean, this word says that the static current, static in the sense like it may be at rest position, velocity zero or something. But the definition of current is the motion of charge. I mean, I is dq by dt. If the charge is moving with respect to time, then we will say that constitutes a current. And if you see combinedly, I mean, if you see that this word crudely in crude sense, rest position charge, rest position current. This word is a little bit interesting. So it is, doesn't mean that that current is at rest position. Steady current in the sense, if any conductor is carrying some amount of current, right, at any particular instant of time, if you measure in any particular instant of, let be this is the point we are interested to measure the amount of current at any time. So if you measure that any time, that amount of current will be constant. So that amount of, I mean, the magnitude of current is not changing with respect to time. So here the study in the sense a constant current, or you can say the value of current is not changing with respect to time. Now this type of source will produces the magnetic field, and we are considering throughout the video this will be the source. So if steady current is this, I mean the steady current which is carried by the conductor is the source, what will be the nature of that magnetic field? So that magnetic field will be in the form of a concentric circles around that current carrying conductor, and we can represent the direction of that magnetic field by a right hand thumb rule. We can visualize that with a diagram, schematic diagram. So now we can explain that for two conditions. So here that current is in upward direction. This is the direction of current. So just place the thumb in the current direction. Then the direction of these fingers, I mean the curl of the fingers will show the direction of magnetic field. I mean, as per this diagram, if current is in upward direction through conductor, around that current carrying conductor, the magnetic field will be generated in like a concentric circles, and the magnetic field will be in anti-clockwise direction. Similarly, if the current is let be in downward direction, so same, place the thumb in the current direction, then the direction of these fingers, I mean the curl of fingers will shows the magnetic field. Now in this case, the magnetic field is in clockwise direction. And some other basic definitions, magnetic flux. So whenever we'll say the flux, the general, I mean this is common definition for any type of fields. Flux in the sense number of field lines. So here that field is magnetic field, so the number of magnetic field lines crossing through a surface is called flux. But this is not the standard way of measuring the flux. The better way of measuring the flux is flux density. So of course, the entire definition will be same. But here we are neglecting particular condition which is perpendicularly. So the number of magnetic field lines passing through the unit area, but of course that field lines must pass it through that unit area perpendicularly. So only perpendicular components of magnetic field lines we should consider to measure the flux density. Or you can say simply like the magnetic flux per unit area perpendicularly is magnetic flux density. So this is flux per unit area. Pi by S will be the B. I mean, we can represent that in diagrammatic view. Let be this is a surface. Let be this is surface. Or it's better to draw another plane. Let be this is a surface. Yes. Now a magnetic field line is passing through that surface like this. Now this is exactly perpendicular to the surface. So we can count this for flux. But it is not mandatory that every line should pass through the surface perpendicularly. It may be possible that line may also passes through that surface with an angle of theta. But here, as per this diagram, that flux will not be 2 because this is perfectly perpendicular to the surface, but this is not. So under such condition, generally what we'll do, we'll just resolve that vector into two components. That field line is resolved into two components. Now this component only is exactly perpendicular to the surface. So approximately it is like a 1.5, flux is 1.5 unit. This is completely perpendicular, and a part of this line is passing through this surface perpendicular. So around approximately 1.5 unit is the flux, right? So that from this equation you can write that flux is equal to B into S. So as per this explanation, now if you see, so this is generalized this is generalized equation. So that pi B, I mean magnetic flux is Bs cos theta, because this is cos theta. This component is cos theta. So Bs cos theta, or you can write B dot S. B dot S. And in some cases it is not possible to measure the flux for the surface. Yes, right? It will be, sometimes it may be difficult. So in order to simplify that, so what we'll do generally, first we will consider a unit, a small segment unit surface, and we calculate the flux d pi through that small surface, and then we'll I mean we'll do that surface integral for that calculation. So that integral form of that flux will be B dot ds. This is surface integral, I mean double integral. Double integral B dot ds. Now this is one more relation between magnetic flux density and magnetic field intensity H. And generally this relation B is equal to mu H. So where this mu is permeability of a medium, And if we take the analogy in electric field, that relation is D is equal to epsilon E. So analogy is magnetic flux density is like displacement vector in electrostatics. Magnetic field intensity is similar to like electric field intensity, and the corresponding components, corresponding constants. This is permeability and this is permittivity. And if it is in free space, if it is in free space, the permeability of free space is 4 pi into 10 to the power of minus 7 Weber per meter square. This is constant in free space. Now we'll come to the Biot-Savart's law. So what is the significance of this particular law? The purpose of this Biot-Savart's law is to calculate the magnetic field induction. To calculate the magnetic field induction at a given point. Of course, this magnetic field is generated because of what? A current carrying conductor. And even we can write the equation not only in terms of P, in terms of H also. I mean, just by using the relation B is equal to mu H. And what is that statement? What is that law by its Savart's law? The magnetic field, the magnitude of this magnetic field dB at any given point is proportional to the product of I current, a small length dl, and the sine theta, ideal sine theta, and is inversely proportional to square of the distance between the current element and the P. So it seems to be like a little bit abstract. So that's why we'll try to explain that through this diagram. Just here. So now you are taking the current carrying conductor in random shape. So in more generalized way, this statement is given. Generalized way in the sense, the shape of that current carrying conductor is taken randomly, and through this current carrying conductor, an I, uh, amount of current of I is passing through that conductor. Now our aim is to find the magnetic flux density at a given point P. At a given point P. Now this P is at a distance of R. At a distance of R from the current element dl. For the current element dl. What does it mean? First we are taking a small segment of dl. Then due to this small length which is carrying conductor, first we will find the magnetic field induction at a point P, and then later on we will integrate that. We will try to calculate that magnetic flux density due to this total length. Right now this vector r, I mean this distance r is made by a base vector r cap. What does it mean? This vector, the distance vector r is made by a base vector or unit vector r cap, just by translating that vector into some number of times. How many times it is? Magnitude of r. So that is mean by vector r is magnitude of r into r cap. And if we consider that small segment dl, then current through this only small segment will be I dl. The total current through this entire length is I, of course, but through only this small segment will be IDL. Now this particular point P is making an angle of theta, with this small segment dl. So if these are the conditions, then the Biot-Savart's law says that the magnetic field induction will be proportional to ideal sine theta. So in between the product is there, and is inversely proportional to square of the distance. dB is 1 by r square. And if you consolidate them, if you consolidate the both equations 1 and 2, then this dB will be equal to what? Ideal sine theta by r square. And we'll remove this proportionality and replace that replace that the constant which is related to magnetostatics, that will be k ideal sine theta by r square, but more exactly that constant will be mu 0 by 4 pi, mu 0 by 4 pi ideal sine theta by r square. Now this equation 5, the equation 5 is helpful to calculate the magnetic field induction due to a current carrying conductor at any point p. But this is only due to what? Only due to a small segment, a small length dl. But if you are interested to calculate that is due to total length, this we need to integrate that. This b will be equal to what? Integral db. Just integrate this equation, so that will give the magnetic field induction due to total length. And even you can write that in vector form also. So you can write this equation in vector form as mu 0 by 4 pi as it is, because they are constants, and this I is a scalar quantity. So where that we cannot do anything in vector form. So electric current is a scalar quantity. But now you can write this dl sine theta as dl cross r cap, dl cross r cap. So if you apply the cross product dl cross r cap, the cross product magnitude is magnitude of dl, magnitude of r cap, and sine theta. You already said this r cap is a unit vector, so its magnitude will be 1 unit. Magnitude will be 1 unit, and this is dl, and this is sine theta. So ultimately you will get dl sine theta. So you can write this dl sine theta as dl cross r cap by r square. So this equation is helpful to calculate the magnetic field induction B. Or you can write this mu 0 as the denominator of B, then you can write that same equation in terms of H also. I mean, if you are interested to write in H, this dH will be equal to 1 by 4 pi, 1 by 4 pi dl cross r cap by r square. And one more thing that you can observe, just this is for the sake of information. So if you compare electrostatics and magnetostatics, uh, the constant related to electrostatics is epsilon, I mean permittivity. The constant which is related to magnetic field, magnetostatics, is mu, which is permeability. And if you see any equations in both electrostatic and magnetostatics, so these two constants are generally reciprocal. Like if you see Coulomb's law, that force of interaction is 1 by 4 pi epsilon naught q1 q2 by r square. So here that epsilon naught is, I mean epsilon is denominator. But for that same concept in magnetostatics, that constant will be in numerator. So they will appear like uh, reciprocal. Now we'll see the Gauss law of magnetostatics. I mean, in lower classes, generally we have a statement that magnetic monopoles do not exist. Magnetic monopoles do not exist. I mean, what does it mean? If you break any magnet, if you break any magnet, we cannot get individual north pole or individual south pole. So they always as a single entity. But whereas for the charges it is possible, you can get individual positive charge or individual negative charge. But in case of magnets, these monopoles do not exist. They will be always like a single entity. And we can try to prove that. We can try to prove that with this Gauss law of magnetostatics, just by applying little bit analysis. So for that, we already said that for that, just see the statement the total magnetic flux through a closed surface is zero. Through a closed surface. What does it mean? If you are saying the surface is closed, it means that surface is enclosing some volume, right? Let be this is randomly we will take a surface, yes. Now this is open surface because it is not enclosing any volume. But if it is enclosing some volume V, now that surface is enclosing volume V. Now this is closed surface. So if any magnetic field lines are passing through the surface, if that surface is closed, of course flux is there, but net flux will be equal to what? Zero. This is possible only for closed surfaces only. So don't ignore this particular term. What does it mean? I mean, you can represent that in equation format. That flux pi, which is B dot ds. See, here we represented that surface is closed surface. B dot ds is equal to 0. We'll try to elaborate that. What does it mean by that? The flux is 0 through a closed surface. So if that magnetic field produced by a steady current through the conductor, we already said that the magnetic field lines will be in the form of a closed loop, right? I mean, let be this is a conductor carrying current I, and due to that conductor, the magnetic field will be produced in a closed loop. So if the nature of magnetic field is a closed loop, so the magnetic field lines are not having any starting point or any ending point if it is closed loop. So we cannot say this particular point is as a starting point, and we cannot say this particular point as an ending point. So there will be no starting and ending point. So if there is no starting and ending point, then the flux line entering equal to the flux line leaving the surface. I mean, if you choose, we'll take a volume. We'll take a volume in that magnetic field. Now this surface is closed surface. Let be this surface is closed surface because it is enclosing this entire volume. Now the number of field lines passing through the surface and number of field lines leaving through the surface will be is equal. So number of field lines passing through that and number of field lines leaving through that surface will be equal, because in another way you can say there is no starting point or no ending point. I mean, we will try to understand this with Gauss law of electrostatics. See there, you can see my previous video there. Let me this is a closed surface, and the surface is enclosing some volume V. Some volume V. Now this surface is also enclosing some charge Q. Some charge Q. Now this charge Q will produces the electric field lines in all possible directions. So in that some field lines are passing through the surface. Here the flux is not equal to 0 because here the starting point is clearly mentioned, that is within the volume. Right? The starting point for that electric field lines is exactly within the volume. So this is only leaving that surface. So in this case, the nature of field lines is only leaving, no entering, because it is not entering from outside. That field lines are generated within the volume. So here the flux will not be equal to 0. But here there is no such origin from where the magnetic field lines are producing. That's what we are saying. There is no starting point and no ending point. So that the total flux will be equal to what? 0. And this is possible only for closed surface. Right? This is mathematical representation of Gauss law of magnetostatics. But from this, I mean, how we can say the magnetic monopoles do not exist? And if you, similar to like Gauss law of magnetostatics, if you write the Gauss law of electrostatics, just see the analogy. So that flux pi is equal to integral closed surface integral, instead of B or instead of H, we will write E. Electric field intensity over a closed surface is equal to 1 by epsilon naught times, or 1 by epsilon times charge enclosed. Charge enclosed. So here the charge may be plus Q or it may be minus Q. So this represents the individual charges can be formed. So there is you can find the individual electric charges, because either it may be positive charge or it may be negative charge. But if you see this equation for magnetic field, there is no such term like which represents the magnetic pole. It is equal to what? Zero. So based on that, we can conclude that from Gauss law of magnetostatics, the magnetic monopoles always do not exist. They will always as a single entity. Now this is in integral form. We already given that. That's closed surface integral B dot ds is equal to 0. And even we can write this Gauss law in differential form also. Differential form also. And for that, just we need to apply the Gauss divergence theorem. The significance of Gauss divergence theorem is you can mutually interchange the surface integral to volume integral, or vice versa is also possible. Volume integral to surface integral. I mean, if you write that mathematically, let f be the f function, vector function. This, if the surface is closed, f dot ds, and it can be written as integral. We are saying that the surface is a closed surface. What does it mean? It is enclosing some volume. So that volume is V. Del dot that vector function f d, right? This del dot is generally represents the divergence. Divergence in the sense spreading nature of that particular function. And of course, it is a mathematical operator. The del is equal to vector operator I dou by dou x. I mean I cap along x-axis. J cap dou by dou y, and k cap dou by dou z. Dou by dou z. So if it is applied with the dot product on any vector function, then it will say divergence. You can say divergence. Now we can convert this into surface to volume integral. If you convert that, just see here, this will be equal to 0 as per this equation 1. You can write this closed surface integral as 0, so that the conclusion is del dot B is equal to 0. So there is no divergence is there through a closed surface, divergence of magnetic field. So this is Gauss law of magnetostatics, both in integral form as well as in differential form. So apparently it is not simply differential form, but I already told you this del is a vector operator, in which here the differential form is there, I dou by dou x plus j dou by dou y k dou by dou z. Right. This is special case of Ampere's law. This is special case of Biot-Savart's law, in the sense. At the beginning of Biot-Savart's law, we already said that the shape of that conductor is taken completely random. I mean, this is unsymmetric. Unsymmetric. If that current is through a conductor and the conductor is in symmetric in nature, then you can apply this Ampere's law. So that's why you are saying Ampere's law is a special case of Biot-Savart's law. Or in another way, you can say Ampere's law is applicable only for symmetrical current, symmetrical conductor which carries the current. But Biot-Savart's law is universal, that we can apply for any current conductor, I mean, which may be in random shape. But what this statement shows, you can represent, I mean, you can define that statement in two ways, either in terms of H, in terms of magnetic field intensity, or in terms of magnetic flux density. So we'll see that both. So just explain this integral that will give the definition of our statement of Ampere's law. So this is a closed line. So this is line integral. That line must be a closed line, right? So that Ampere's law states that the line integral of magnetic field intensity, the line integral of magnetic field intensity over any closed path, closed line, or you can say closed path, is equal to the amount of current enclosed by that path. I mean, I mean just see here. Let be this is current carrying conductor. Now see that now almost nearby. The shape of that current conductor is not randomly. I just try to draw as straight as possible. Now this is symmetry. If conductor is straight, the shape of the magnetic field will be exactly circles, right? Now this is closed path because this line is enclosing some surface. So this is closed path. But now the same surface is open surface because it is not enclosing any volume. But now we are just focusing on that path is a closed path. It means it is enclosing some surface, right? So overall, I mean, if you see the overall statement of this Ampere's law, so the total magnetic field intensity over a closed path is equal to the current enclosed by this path. Current enclosed by this path. So you can write enclosed current. Or even you can define that in terms of B also. The definition is same at the left side. Instead of magnetic field intensity, we'll say magnetic flux density. So the line integral of magnetic field induction or the line integral of magnetic flux density over any closed path is equal to mu naught times to the current enclosed by the closed path, right? So you can write that equation both in magnetic field intensity or magnetic flux density B. And we will try to see two applications where we will apply this Ampere's law to calculate HRB. So the first application is, let we'll calculate the magnetic field intensity due to infinite long straight conductor. Infinite long straight conductor. So there will be an infinite long straight conductor, and this conductor is carrying some amount of current, and randomly we will say the direction of current is along the z direction, and this current will produces the sorry, this current will produces the magnetic field around this conductor, and in that region randomly choose a particular point P, right? Now we need to determine the H by using Ampere's law. I mean, we can show that diagrammatically like this, right? I mean, this is conductor. Now this conductor is producing the magnetic field around that conductor in concentric circles. So now all these concentric circles are like a closed path. Now in that you are choosing a particular closed path, and you are calculating the H for this closed path, and the direction of current is let be in Z direction. It is not mandatory in Z, but just randomly we choose the direction as in Z direction. So in order to calculate that, first we'll select a small segment of DL on the closed path. In that closed path, first we'll select a small segment of DL. Then we'll calculate the amount of magnetic field intensity DH. Of course, this dH is due to what? This current carrying conductor. Then if you integrate this for over to complete length, I mean instead of dl, if you integrate that for this entire path, that will give the total magnetic field intensity due to that current carrying conductor. Right? If you see that as per Ampere's law, the line integral of or you can say contour integral, or you can say closed path, the line integral of magnetic field intensity over a closed path is equal to I mean the current enclosed by that path. But if that shape of the conductor is straight, the nature of magnetic field will be circular in nature. Circular in nature. If the shape of that magnetic field around the conductor is circular in nature, then if you select any point on that path, the distance will be same, because radius is same for a circle. So if all the points are at same distance, then this h will be definitely constant, right? Because on the circular path, to that circular path for any point, the distance between that current and that point will be at any point will be same. So magnetic field intensity will also be definitely same. I mean this is constant. If it is constant, you can write the out of the integral. You can write the out of the integral. So you can write that h out of the integral, and this is closed path dl. If the path is in circular shape, so just we need to write its perimeter. So that perimeter will be h into 2 pi r. I mean the total length of this circular path will be 2 pi r, and of course this h will be equal to what? I by 2 pi r. I by 2 pi r. Or if you are interested to write in terms of b, just apply that b is equal to mu h or mu 0 h if it is free space. So instead of h, we'll write b by mu. So now this equation will change to b by mu is equal to I by 2 pi r. Or you can write this b is equal to mu by 2 pi r into I. I enclosed by that path. Sorry. Now we'll extend that problem. I mean, we'll apply that Ampere's law. Now, but this is the two-dimensional current source due to infinite sheet of current. Like the current is through through the paper. It is a two-dimensional object. So let me first we'll consider the infinite long sheet in z equal to 0 plane. In z, so through which sheet that current is passing, let be z equal to 0 plane. I mean if you say z equal to 0 plane, or you can say xy plane, xy plane. In the sense, just consider the floor in your room. So let be that floor is xy plane. Then on that floor anywhere that z value will be 0. So you can represent that floor in two ways. Either you can say xy plane or z equal to 0 plane. Right? Now the current is passing through that sheet in y direction. Along the y direction. Then the current density is written as, so if current is along the y direction, the J is equal to J by AY. I mean where this AY cap is the unit vector along the y direction. Like j cap is unit vector along the y direction. Instead of j cap, we are just writing this as ay cap. This is base vector or unit vector. Right, now consider a closed loop 1 2 3 4 1 perpendicular to the current direction in which that exact plane is shown figure. I mean in order to understand this statement, first we'll try to go with figure diagram, then it is easy to understand this particular statement. Now see all these conditions in this diagram. So now let be this is sheet. Let be this is sheet. So through this sheet, the current is passing. So first, in order to explain all this, first we need to fix the frame of reference. We need to fix the frame of reference. So generally we use the Cartesian coordinate system, which consists of three directions, and the three directions are mutually perpendicular. This x-axis, y-axis, and z-axis. So just we'll keep that frame of reference on that sheet, which carrying the current. And these are base vectors along the x direction, y direction, z direction. So ax cap is the unit vector along x, or you can say generally you'll say I cap or ax cap. Similarly, ay cap is the unit vector along y direction, and az cap will be the unit vector along the z direction. So now see, on this sheet anywhere the z value will be 0. So that's why we are saying z equal to 0 plane or xy plane. Now through that sheet the current is along which direction? Y direction. So now this is y axis. We define this particular direction as y axis. So that's why we just notice that the current is along the y direction. The current is along y direction. So then the current density will be equal to what? Jy ay cap. Now consider a loop, a closed loop. I mean closed path. So let be 1, 2, 3, 4, 1. So now this is closed path, and you are taking that closed path in which direction? That perpendicular to the current direction. Just see there. Now this path is exactly perpendicular to the current direction. What does it mean? Now this closed path in which plane? This is the direction of x-axis. I mean let be 3, 2 is one of the side. 3, 2 is along x, and 3, 4 is along z. So this is in xz plane. So what does it mean? Simply you can say you are considering a closed path like 1, 2, 3, 4, 1 perpendicular to the current direction. Right? I mean why we are taking in xz plane? Because as per our earlier discussion, if this is the current, let be y direction, if this is the current y direction, that magnetic field will be generated in a plane perpendicular to this direction, perpendicular to this current direction, right, which is xz. So that's why we took that particularly in xz direction, right? And if you see this particular closed loop in detail, so 1 2 is along z direction, so that's why it is minus hz. 1 2 is a downward direction, so the magnitude will be minus hz. And 2 3, 2 3 will be minus x, because it is like inwards, it is inwards, so minus hx. And 3 4 is in positive z, so the magnitude will be hz. And 4 1 will be the x direction, that what we define, that's why it is plus hx. And this is the direction of the current density j, enclosed, because this current is enclosed by this closed path, right? This is about the diagram. Now we'll see. So that as per the current enclosed by the loop will is equal to what? The current crossing the distance is given by I mean sorry, the current crossing the distance b is given by I enclosed is j by b. We'll try to explain that, right? As per Ampere's law, as per Ampere's law, this is Ampere's law. The closed, I mean magnetic field induction over a closed path, magnetic field intensity over a closed path is equal to I enclosed. and we are saying that I enclosed as jy into b. But we need to note 2 points. Sorry, we need to note 2 points here. So if you apply the right hand thumb rule, these are the two key points when you are calculating the magnetic field intensity due to infinite sheet of current, where we should not ignore this. So from the right hand thumb rule, the magnetic field along the z direction will cancels each other, right? This is first one. And also the magnetic field intensity have a component along the cannot have the component along the y direction. So out of three directions, so there is no component along z and no component along y. So only x component of magnetic fields are non-zero, because rest of the two directions the magnetic field intensity will be zero. What does it mean by that? What does it mean by that? Just we'll try to explain this particular statement with this diagram, right? So as per our consideration, this is the direction of j. I mean, which direction? Along the y-axis, right? We define this particular direction as y-axis, and of course, this is x-axis, right? And this is z. So two such current paths. We consider two such current paths of j, and for this particular current path, this will be the closed loop. This will be the closed loop, because the magnetic field will always be perpendicular to the current direction. I mean, in a plane perpendicular to the current direction. Similarly, if this is the direction of current, this will be the closed loop. Now just see the z component of that magnetic field. Here it is downwards, hz, because here we shared this particular path 1 2 3 4 1. Similarly 1 2 3 4 1. So for this particular closed path, hz is in downward direction. Adjacent to that hz is in upward direction. So what will happen? Both these components will cancel each other. Similarly, this downward direction hz, if you consider one more current, so that will be cancelled with adjacent. So everywhere that magnetic field intensity along the z direction will be cancels each other. So there will be no magnetic field along the z direction, right? Number two, H cannot have components along y direction, because from the beginning we are saying that if this is the direction of current along the y axis, the magnetic field will be produced perpendicular to the current direction. I mean, this is xy plane. What does it? Sorry, xz plane, because which plane will be perpendicular to y? Xz. So what does it mean? There will be no magnetic field component along the y-axis, because this is the direction of current. The magnetic field always be in a plane perpendicular to the current direction. So that's why there will be no components along the y direction. So the magnetic field will be only in one direction, that will be x. That will be x direction. So if you see the x, y, z, for which quantity? Magnetic field intensity. This hz is 0 because of cancelling each other, right? Y component of that magnetic field will be 0 because in that particular direction current is there. So there will be no magnetic field components. So only hx will not be equal to 0. We will see that, we'll calculate that. So just I took that these diagrams from previous slide just for the sake of understanding. Now see here. So now we need to apply that Ampere's law for this much number of paths. Total how many number of paths in that closed path? 1 2 is the one path, 2 3 is the second path, 3 4 is the third path, and 4 1 is the fourth path. So now this closed path is divided into four line segments, right? 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So we'll apply this h dot dl for each and every path. Just here, 1 to 2. 1 to 2 is along which direction? Z. But it is downwards. The arrow mark is showing that along the downwards. So what is its magnitude? Minus hz, right? And what is the length? We are saying that length is equal to what? Length of that path is a. Now see there, right? So hz minus hz minus hz into a. Similarly, see that 3 to 4. 3 to 4 will be plus hz plus hz a. So these two will be cancelled. As we said previous slide, the z component will be cancels each other. So remaining will be two paths, which is 2 to 3 path and 4 to 1 path. If you see 2 to 3 path, the width will be b, but inwards x direction, so minus b. And it is inwards x direction, so the magnetic field is minus hx. So this integral will be minus hx minus b. And for 4 to 1 path, these are exactly the defined x direction, so both will be positive. So this is in its x direction and length will be b, so hxb. So the right hand side, the total value will be 2hxb, which is equal to the magnetic field intensity over a closed path, right? So from equation 2, which is previous and now, this h dot dl, instead of h dot dl we are giving this as 2hxb, because which is equal to what? This h dot dl is equal to I enclosed. I enclosed, we define this I enclosed as jy into b. So this 2hxb will be jy by b. So on both sides b will be cancelled, so that hx will be jy by 2. Hx will be jy by 2, or you can say in vector form jy by 2 ay cap, right? This is magnetic field intensity due to um, infinite sheet of current. Or if you are interested to write in magnetic field induction, just apply that b is equal to mu h. So instead of h we'll write b by mu, so that this equation will change to this b is equal to mu by 2 jy, right? This is the second application of Ampere's law. Thank you.